Long before predators ruled by teeth and claws, ancient parasites perfected a deadlier art, destroying their hosts slowly, efficiently, and from the inside. Paliox urus cockburni, a 240-million-year-old pinworm inhabiting cynodont proto-mammal intestines, executed death through nutritional starvation rather than direct tissue destruction. The worm's thread-like body, measuring 2 to 5 millimeters long, allowed silent navigation through intestinal folds, while a multi-layered cuticle provided protection against digestive enzymes. The killing mechanism was elegantly indirect. Paleoxyurus specialized in colonizing cellulose decomposition chambers, where symbiotic microorganisms broke down plant material into absorbable nutrients. By systematically consuming these beneficial bacteria and protozoans, the worm transformed the host's gut into a non-functional digestive system. The host continued eating normally, but extracted progressively less nutrition from each meal as its microbial workforce vanished into the parasite's gut. This created chronic malnutrition, manifesting as stunted growth, weakened bones, muscle wasting, and compromised immune function. Infected cynodonts became smaller, slower, and more vulnerable to predation. Death arrived through starvation. Despite full stomachs, the host literally ate itself to death while the parasite thrived on stolen microbial resources. Eggs discovered in Brazilian coprolites reveal a 2-layered shell with a distinct polar cap, unchanged across hundreds of millions of years from ancient reptiles to modern primates. This silent nutritional sabotage proved devastatingly effective, but lacked the dramatic blood extraction of our next parasite. Dinocraton draculae, the Cretaceous-era tick, preserved in 99-million-year-old amber, killed through catastrophic blood loss, amplified by nest-based population tactics. An engorged female specimen shows body volume expanded 8.5-fold beyond baseline, representing blood extraction equivalent to multiple times the tick's original mass. The deeply pitted exoskeleton allowed extreme expansion without rupturing, functioning as a biological storage tank. Backward curved mouthpart barbs anchored into skin, creating sealed feeding channels. Specialized salivary compounds prevented blood clotting while suppressing immune responses, allowing uninterrupted feeding for hours or days. A single feeding session could extract 10 to 15% of a juvenile dinosaur's total blood volume. This acute blood loss triggered immediate physiological collapse, plummeting red blood cell counts, reduced oxygen delivery to vital organs, causing lethargy, hypothermia, and potential cardiac failure. The open wounds created by attachment served as bacterial entry points, frequently causing secondary infections more lethal than initial blood loss. What transformed Dinocraton from nuisance to killer was its nidicolous lifestyle, permanent nest residency, confirmed by dermestid beetle larval setae adhering to tick bodies. Instead of single parasites attacking isolated hosts, entire tick populations concentrated in nesting areas. When parent dinosaurs returned to roosts, dozens of engorged ticks simultaneously fed, collectively draining 20 to 30% of available blood volume within hours. Repeated attacks over weeks created cumulative anemia, immune exhaustion, and progressive weakening. Hatchlings and juveniles suffered disproportionately. Their smaller blood volumes meant even modest tick loads proved fatal. The expandable integument enabled resource extraction that turned safe havens into death traps, though this brute force vampirism lacked the surgical precision of our next parasite's reproductive sabotage. Invavita piratica, a 425-million-year-old tongueworm from the Silurian period, killed by simultaneously draining bodily resources and obliterating reproductive futures. Fossils preserved in Herefordshire volcanic ash reveals specimens attached externally to ostracod shells, while others resided internally near egg sacs, a dual-location assault offering no refuge. The external attachment system employed specialized limbs and a proboscis clamped onto the carapace, creating constant drag during swimming. This forced the host to expend 2 to 3 times normal energy for locomotion. The metabolic cost accumulated rapidly. Ostracods burning excessive calories for basic movement entered chronic energy deficit, depleting fat reserves and muscle tissue to fuel survival. Internally positioned specimens executed more devastating exploitation. The elongated proboscis and articulated limbs allowed navigation through soft tissues to reach the egg sac, the most nutrient-dense structure in the host body. Invivita consumed developing eggs directly, appropriating proteins, lipids, and minerals concentrated for offspring production. Each consumed egg represented not just lost nutrition, but erased genetic legacy. This parasitic castration created a grotesque metabolic loop. The host continued investing energy into egg production, but all resources flowed into parasite growth rather than reproduction. The ostracod became a biological factory optimized for feeding its killer. Over weeks, the combined external drag and internal consumption created terminal energy bankruptcy. Unable to feed efficiently due to impaired mobility, stripped of reproductive reserves and hosting a growing parasite consuming calories faster than the host could acquire them, death arrived through multi-system starvation. The dual internal-external attack system represented evolutionary genius guaranteeing nutritional collapse, though it lacked the tissue-destroying brutality of our next contender. Cephalus dauhugoensis, the 165 million-year-old thorny-headed worm, killed through devastating mechanical intestinal destruction and direct nutrient theft. The retractable proboscis, armed with approximately 26 spiral rows of backward curving hooks, totaling 650 to 780 individual barbs, functioned as an irreversible anchor. Once embedded in intestinal lining, the hooks created hundreds of penetration wounds. Each peristaltic contraction attempting to expel the parasite drove hooks deeper, shredding mucosal tissue and severing capillaries. Chronic intestinal bleeding caused progressive anemia as the host slowly bled internally. What made Cephalus uniquely lethal was its retention of functional jaws and digestive tract, features lost in modern descendants. The double rows of tooth-like structures actively chewed intestinal lining, consuming tissue at the attachment site. This created expanding ulcerated craters where digestive enzymes leaked through damaged barriers, causing chemical burns to surrounding organs. The worm's 23.4 millimeter size meant substantial intestinal blockage, preventing proper food passage. Nutrients absorbed upstream never reached lower intestinal sections, while downstream sections received only parasite waste products. The host experienced starvation despite eating, as calories were either blocked from absorption, consumed by the parasite, or lost through bleeding wounds. Death progressed through multiple pathways: severe anemia from chronic hemorrhaging, septic shock when intestinal perforations allowed gut bacteria into the bloodstream, and nutritional collapse from combined malabsorption and direct tissue consumption. The proboscis hooks transformed the host's own digestive contractions into a self-destructive meat grinder. But even this mechanical brutality pales before our final parasite's complete neurological hijacking. Paleoophioccordyceps gerontoformicae, preserved in 99-million-year-old Burmese amber, killed by transforming the host into a mobile feeding platform before strategic termination. Upon contact with an ant's exoskeleton, fungal spores deployed chitinase and protease enzymes, dissolving the armor at molecular levels. Inside the hemocole, yeast-formed cells circulated through hemolymph, absorbing nutrients directly from the host's circulatory system, creating immediate caloric deficit as the ant's metabolic fuel was siphoned continuously. The fungus produced cysteine-rich peptides targeting calcium-dependent scramblase channels in neuronal cells. These compounds disrupted motor coordination and paralyzed olfactory navigation, preventing the ant from following pheromone trails to food sources. Unable to forage efficiently, the ant entered accelerating starvation while the fungus grew exponentially on stolen calories. The killing mechanism's genius lay in precise timing. The fungus hijacked circadian rhythms and phototaxis responses, compelling the infected ant to abandon its colony and climb to elevated positions with optimal temperature and humidity for fungal reproduction. This forced march occurred during late-stage infection when the ant's body was completely colonized, a hollow shell of insect tissue surrounding a growing fungal mass. The death grip followed. Fungal toxins triggered irreversible mandible muscle contractions, forcing the ant to bite into leaf veins or bark. Anchored in position, the fungus delivered final mycotoxins that terminated host life. Post-mortem, the fungus transitioned to filamentous form, consuming remaining internal tissues before erupting through the head as a sporocarp releasing thousands of spores. The peptide-based neurological control system represents the ultimate parasitic weapon, erasing autonomy while preserving bodily functions until strategically optimal. The ant died not from tissue damage, but from complete metabolic commandeering, every calorie redirected from host survival to fungal reproduction. In the hierarchy of biological horror, nothing surpasses the theft of consciousness itself, transforming complex organism into a mindless spore dispersal automaton. And that's the real horror of ancient parasitism, not violence, but theft of energy, of reproduction, of control, even of the mind itself. These creatures didn't need claws or fangs to dominate life on Earth. Patience and precision were enough. If you found this descent into prehistoric biological horror unsettling, fascinating, or both, make sure to like the video, share it with someone who loves dark science, and subscribe for more stories where evolution turns survival into something far more terrifying. See you in the next layer of deep time.